In this section, we discuss electron and hole recombination, which is important for understanding the operation of LED lighting and solar cells. Recall that electron and hole pairs are created when an electron in the valence band is excited to the conduction band. This requires an energy of at least the band gap, which can be supplied either by a photon of light, called photoexcitation, or just from the thermal energy in the system, called thermal excitation. On a band diagram, E versus K, where h bar k is the electron momentum, a simple photoexcitation is a near vertical transition because of momentum conservation. The momentum supplied by the photon should be the change in electron's momentum. However, the momentum of a photon is very small because it has no rest mass. Recall, a photon momentum is h over lambda, which is the energy E divided by the speed of light c. Since c is very large, the momentum is very small. Thus, on the scale of an electron band diagram, the electron transition, including conservation of momentum, looks vertical, as if there's no change in k. An electron excitation across an indirect band gap is not a vertical transition, so it requires another particle, typically a phonon, for momentum conservation, making the process more complicated and therefore less probable. While excitation is the generation of electron and hole pairs, recombination is the opposite process where an electron in the conduction band fills a nearby hole in the valence band. This then releases a photon of light with energy equal to the energy lost by the electron. This destroys both the electron and hole in the process. In the block diagrams, the transitions are vertical because the electrons and holes must be physically close in a similar location in space for the transition to occur. Direct transitions occur easily in a direct band gap semiconductor because the electrons and holes collect at the same momentum k. Electrons are most likely to be found at the conduction band minimum, while holes are most likely to be found at the valence band maximum. This gives the maximum probability for an electron to find a momentum-conserving hole to drop into. Recombination is slower in an indirect band gap material such as silicon because most of the electrons and holes have different momentum. A vertical transition is forbidden because the momentum-conserving states are occupied. Recombination then requires an additional particle, typically a phonon, to change the momentum and enable the transition. Recombination can be facilitated by a recombination center, which is typically a defect that produces a localized energy level within the band gap. The free electron or hole can then recombine in a multi-step process where each step is a lower energy transition with higher probability than direct recombination. Such defect sites can also act as trapping centers where the electron or hole is localized only temporarily before delocalizing again. This can slow the charge carrier, reducing mobility and mean free path, as well as reducing the local free charge carrier concentration. Recombination can be characterized by a recombination time like a half-life for radioactive decay. For example, imagine a semiconductor that is illuminated for some time and then the light is turned off. In the dark, there are thermally excited electron and hole pairs making free positive and negative charges, but also excess free carriers or holes due to impurities or defects. Here, excess electrons from n-type doping. In this case, the electrons are the majority charge carrier and the holes are the minority charge carrier. During illumination, electron and hole pairs will be formed, so there will be more of both electrons and holes, although the relative increase in holes, the minority charge carrier, is more noticeable. So we will follow the minority charge carrier concentration, here the hole concentration P in this n-type material, written as P sub n. We will call the increase in P delta P sub n, which rises linearly and then saturates at some constant level. When the light is turned off, the excess hole concentration will fall back to the dark value due to recombination, but it may take some time for the holes to find an appropriate electron. The recombination rate can be directly measured and characterized by a time constant tau we call the recombination time. Because the recombination rate of holes should be proportional to the concentration of holes, dp dt is proportional to p over tau, the hole concentration should decay exponentially with time constant tau. Since this recombination time is most noticeable for the minority charge carrier, it is also called the minority carrier lifetime. During illumination, it is also this minority carrier lifetime which limits how many excess charge carriers can form. Under constant illumination, the system reaches a steady state where the rate of photo-generated electrons and holes is exactly compensated by the recombination rate. Thus, a long recombination time means that for a given photo-generation rate g, the increase in change in carriers delta p also depends on tau, here called tau h because it is the whole recombination time.